Today we have Dr. Yair Pinto giving us a talk on the can non-random collapses of the wave function enable libertarian free will. And I already pasted this abstract and bio into YouTube, and also I'll paste it to the Zoom participants here in chat box. So if you're interested, you can take a look. As far as I know, Yair is by training psychology slash cognitive science slash neuroscience, right?
I did get my master's in physics, but yeah, I got my PhD in cognitive psychology.
Yeah. And as I kind of informally mentioned, Yair is always fun to talk with, and his talk at the conference is very clear and insightful. And that's why I invited him to give a talk on this, kind of controversial topic of quantum mechanism and the free will. I'm looking forward to it. Please go ahead and share the screen.
Yes, thank you now. Right, let's see, share screen. Wait, no, this is not good.
Right.
Differently. Right, so I guess you can see my screen now.
That's a probably speaker view.
Yeah, so I do this on purpose so I can see my notes.
Okay.
All right, thanks again now for giving me this opportunity. And indeed, so this talk is basically about libertarian free will. And yeah, so let me just give you the overview of the talk. So what I will talk about first, I will discuss what do I mean by free will. And then I'll go into the question of, is this even an interesting question? Is this not already solved? So should we even bother with this question? And then I'll argue that, so I'll argue, of course, that it's not solved. I guess, yeah, it's pretty easy to get you on board with that. And then I'll argue, okay, how can we make progress on this? So this, of course, is a question that interests a lot of people. And it's not the lack of interest, there's no research being done to it. It's just, it's very hard to actually do research into this. Then finally, I'll talk about current experiments. And indeed, in the current experiment, as is clear, there will be a heavy role for all kinds of detailistic physics. Yeah, I'm also very curious to hear your feedback on that. Oh, and before I go on, actually, so I wrote down here my name and email address. So if based on this talk you feel that you have questions or suggestions or what have you, feel free to contact me. So this is also one of the purposes of this talk, is to actually get feedback on these ideas, and I'm just very happy to yeah, take on board any suggestions. All right, so I'll start with defining what I'm talking about. So because there, of course, as you guys know, philosophers, and not just philosophers, but also lay people, you can have many different definitions of free will. And so we have to be clear what kind of free will I'm talking about. And I'm talking about the most extreme case of free will. So I'm not talking about compatibilist free will, you know, that you can do what you want or you can think about what you do or whatever. I mean, of course, compatibilist free will exists. I don't think this is for me, this is not the core of the debate. The core of the debate is really agent-causal libertarian free will. Does that exist or not? And there's a very interesting divide here to start with, so I'll define it in a second. But if you do if you send out questionnaires, what you find is that most lay people, and with lay people I also mean students, basically anybody not heavily involved in the philosophy of free will, most lay people, and it's around 80%, and it's basically in every country where you test this, they believe in agent-causal libertarian free will. And then when you do questionnaires with philosophers who study this stuff, it drops to like 10%. So there's a big divide, and I would argue if you look in if you would do the same thing with neuroscientists, most do not believe in agent-causal libertarian free will. So there's an interesting divide here between what people generally think and what the experts think, so to say. Okay, so what do I mean by agent-causal libertarian free will? The idea of agent-causal libertarian free will is that when you choose between two options, you decide. So before you decide, it is really open what will happen. In other words, there's a gap in the causal chain before and after your decision. So it's not, oh yeah, there's some illusion of this agent-causal libertarian free will claims. No. Really, before you make the decision, it's really not determined yet what will happen. And the other, and that's the agent-causal part, is that you decide what happens. So it's not some random event. It's not a random number generator, whatever. No, you are the ultimate cause of your own decisions. And of course, that's the crucial part, because the alternative is that factors beyond your control, such as your genes or your upbringing, or genes, upbringing plus random noise, that they control what you do. Okay, so to just spell this out a little bit more, because there's sometimes some confusion about this. So the idea of determinism.
Sorry, can I?
Yes, of course. Yeah.
I don't remember if we agreed that questions along the way are possible or not, but
let me clarify. So short questions are possible, and clarification questions, of course, are possible. But if you have like a long comment, it's better to save it for that.
No, it's just a short clarification. What does libertarian have to do with? I don't understand why libertarian.
Right. Okay. Oh yeah. So the word libertarian here might be confusing because it's also a political idea. So it has nothing to do with political idea. Libertarian just means liberty, basically. So agent-causal liberty is basically what it means.
I mean, but it's why do you need it when you have free there? I mean, this is you have free.
No, you're right. So so that's kind of a nomenclature. I don't know the exact history of this, but indeed you should just say agent-causal free will. It would be equally clear, or probably even clearer. But for some reason it evolved into that, because there's all kind of compatibilist ideas of free will, where free will is redefined in such a way that you basically do not choose. So basically everything is still determined, but you call it free will for, well, some weird reason. So that's basically the reason, but you're right. That's kind of confusing for many people. Okay, so basically just to reiterate here, and just to make sure that we all get what the topic here is here. So determinism says external factors determine behavior. So there's sometimes this rhetorical trick where people who defend determinism say, yeah, well, either everything you do is determined by fixed factors outside of you or by random factors outside of you. But in both cases, you're not in control. Yes, of course. You don't get free will by being controlled by dice of the rule. That's clear, but that's not the discussion, of course. So the discussion is not, are you controlled by fixed factors or by random factors? No, the question is, are you completely controlled by factors beyond you? Or is it the case that in some cases, to some extent, you are a first cause? You are the ultimate decider, and factors beyond you don't completely. So of course they influence you. So there's another red herring here. It's like, so you say there's no effect at all of your genes or upbringing. No, of course, clearly there is a big effect of those things. The only question is, do they determine everything and you are basically a puppet? Or do they affect you to a large extent and you still have some possibility to affect the cause of events?
Hey,
course of events. Yes.
Clarification question again. Here, external or first cause of a chain. What happens when this is actually part of your brain? Is it considered as an internal to you or external?
No. So the fact that it's part of your brain doesn't automatically make it internal. So there are many parts of your brain. So this is a good question. So it's really you as the experiencing subject. And I haven't even defined whether you are your brain or you're part of your brain. That's not even at stake here. So it's definitely not, your brain decides. Because it could easily be, of course, that there are factors in your brain that you have no control over. So if there are factors that you have no control over that determine what happens, then that's the idea of determinism. Okay. So it could be, let's say we have subcortical areas in your brain that ultimately decide everything you do. Well, it's clear that what happens in subcortical areas is completely beyond your control. So this would mean that everything you do is completely beyond your control. So it's not defined in brain terms yet.
Okay.
All right. So I hope that this is at least somewhat clear. Now I'll go into, is this not already solved? Because there are two reasons. There are two recurring ideas that basically say this is a non-discussion. And the idea is then, libertarian free will simply cannot, or agent-causal free will simply cannot exist. It's just some pipe dream, some layman's fantasy that simply cannot exist. So the first one is a philosophical idea, and the second one is an empirical idea, and that has to do with the work of Libet and many experiments that followed up in that. So philosophically, there's this idea, some people have put this forward, so what is crucial here in this definition of free will is that not everything you decide is determined by factors beyond you. Because if factors beyond you decide what you do, then ultimately you're not in control, of course. But that means that you, to some extent, have to be a first cause. And there's this general argument, people say if first causes cannot exist. That simply contradicts the idea of cause and effect. And basically the idea here is every cause requires another cause, right? So you cannot be a first cause because when something causes something, it needs to be forced to cause it. It needs another cause. Okay, and empirical ideas, but Libet already showed that what you do is predictable before you do it, so you don't have free will. Okay, so I'll just go over these shortly, especially the philosophical one. I think this is basically not a rock solid argument. So the idea is first causes cannot exist. Well, it's true that by definition, effects require causes. That's just how we define it. An effect is caused by something else. But that's not true for causes themselves. So the definition of a cause does not imply that it requires a cause as well. But okay, set aside definitions, that's just stuff we make up. But you can also say, wait a second, we can actually turn this around. What if there can be no first causes? So this is also a well-known argument. Then you always have an infinite regress. So that then each cause you find requires another cause ad infinitum. You'll never get there. So every event that is there requires an infinite chain of causes. And you might say, I'm fine with that, but it's not completely clear that that's such a great option either. So I would say that let's put aside for the moment philosophy, at least this philosophy. Because it's just simply inconclusive. Yes, we can have strong ideas or strong intuitions, or I've also seen discussions where people say, introspectively, I just feel that I don't have free will. Okay, so this might feel very true, and there might be philosophical hunches that you feel a strong connection to, or it might be the other way around, of course, that people say, but introspectively, I just feel that I have free will, but at this point, that is inconclusive. So we cannot say, okay, the discussion is over just based on these inconclusive hunches, I would say at least.
So I find it hard to accept that there cannot be a first cause. Is there a clear intuitive argument for why that might be? Because as a physicist, I'm a Big Bang, you know.
Exactly. So I don't agree with that idea, but so I'm arguing against that idea. So that the idea that you say there cannot be a first cause, that's basically what some philosophers have put forward. So I don't want to go into it too deeply, but I of course agree with you that this requires strong proof. You cannot just put that out there as an axiom, as an axiomatic statement, and it sometimes is put out there as an axiomatic statement. And I would say, okay, that's probably a hunch that some people feel very strongly. The idea is a little bit the cause and effect idea, right? Like if something causes something else, then of course it needs another cause. How else can it be? So, I mean, I cannot completely relate to that either, but that's basically an intuition that some people have. But I agree with you. Look, if you look at it strictly rationally, that's not a conclusive argument yet, at least. Okay, and then the other argument, which I'll spend a little bit more time on. So this is, I'm not sure how familiar you guys are with it, but it's generally a very well-known result that has received a lot of attention, and it's one of the big discussion points in philosophy of free will. And these are the results of Benjamin Libet. So what did Libet do? People had a simple decision. They had to push a button or not. So they decided themselves freely, decide to push a button or don't push a button. Or in another version, push a button with your left hand or push it with your right hand. And the interesting thing was they had to look at the clock and they had to say when they made the decision. And at the same time, their EEG was recorded. And what you find is they say, this is always called W, when they become aware that they made a decision. And it's approximately 200 milliseconds before they actually execute their action. But you see that the readiness potential builds up way before that. And here is 550 milliseconds. It's a lateralized readiness potential. But you also just have a general readiness potential. That's even like 1.5 to 2 seconds earlier. So then the reasoning is very simple. So this is a very free choice. Basically, freest choice that you can imagine. There's no constraints at all. Just push a button or not. No pressure at all. And this even can be predicted before people do it. So if you can predict the most free of choices that is out there, well, if you can predict it, it has to be predetermined, right? It has to be already. It's not that it's not the variable is already set before you think you will set it. You don't set that variable then, because it's already determined what will happen, predetermined. Before you make your decision, apparently it's already determined what will happen. You think, oh, I might push the button or I might not, but we can look at your brain and say, before you make your decision, yeah, you will push the button. So that would be a very strong argument against free will, of course. If we can fully predict your decisions before you make them, your free decisions, then clearly they're not free. And clearly you don't have agent-causal libertarian free will. Okay, well, there are many problems with Lip's paradigm, so I cannot.
Sorry, was it able to be replicated, this experiment?
Yeah. So this has been replicated an awful lot of times. So, I mean, this is a whole, basically, this is a field in itself. And I think there are literally hundreds, maybe thousands of studies being done into this. And it's a very solid finding. So it's this has been replicated God knows how many times. So yeah, there's no replicability problem here.
Thanks.
But yes, but there are many other problems with Lip's paradigm. So I won't go into all of them. I'll just name one, and then I'll generalize to why I think it's not only not conclusive, but it's basically a line of research that will not help us. Okay, so one of the problems is, what are you actually asking the participant to do? So basically what you ask them to do is to produce a random sequence. And we already know that people cannot do that. So, and you also, the instructions are also much more specific than that. So if you would ask me to basically, so that's what I have to do, right? If I have to push a button or not, or push left or right, I basically have to produce a random sequence, as random as possible. So I could use, of course, an external source for that. So I could just use a random generator or whatever, and that would be very good. And it's kind of funny because these kind of things do come up in reality. So I don't know if you guys are somewhat familiar with poker, but in poker, it's sometimes very useful to be produce random behavior. And poker players really use external sources for that, because they know they cannot do that themselves. So they use some kind of random generator to decide in hands whether they will bluff or not. So yeah, I could do that. Then, of course, you cannot predict anything based on my brain activity. It will never work. So, okay, that's not allowed in the experiment. Another thing that I could do is I could think, okay, well, you know what? I'll just decide at the start of the experiment, I'll push the button every minute. Exactly when the seconds are 0, then I'll push the button. Then this experiment won't work either. And that's also not allowed. So what you're told to do is produce a random sequence and somehow rely on some internal source that generates randomness. Yeah, this in a way is like a very, it's not the freest of choices by any stretch, and it's pretty far away from what we normally consider to be free choices. And as I said, like, first of all, people are really bad at it. So there was a paper out and didn't really get a lot of attention. I think it was in Frontiers. So when you look at the Libet task and you try to predict what people will do, let's say they push left or right, you try to predict if they push left or right based on the EEG signal. Well, chance is 50%. And if you use the EEG signal, you can get up to 60%. So somewhat above chance. If you look at their previous behavior, you get up to 65%. So because people are so bad in making these random sequences, some people alternate way too much, or that some people don't alternate enough. So it's less common, but mostly people alternate too much. So you can basically, based on their previous choices, already predict what they will do with 65% accuracy. And the final thing that I want to say about this, well, what you ask people to do is find some kind of internal source of randomness and rely on it. That's basically what you have to do. If you're not allowed to pre-plan it, if you're not allowed to use an external source, you basically are forced to use an internal source to generate random numbers, so to say. And all you have to, the task now for you to predict what they will do is find which source they use. And if you can find that source, you can basically predict what they will do. So it's not, I think, the most suited task, because it doesn't get into what is really involved in free will, is this decision stage, where you really are pondering or consciously deciding between two alternatives, in a more direct way. But there's actually a much bigger problem than this. So let's say we would do Libet's task, and we say, okay, we don't do the random number generator, we do meaningful decisions. So it's a paper that was published recently by Uri Maos and colleagues, where they found, hey, if you let people make meaningful decisions, something's at stake, so it's not extremely meaningful, but somewhat meaningful, basically predictability goes down to 50%. So in this specific case. Okay, but we can do all kinds of variations with, and they have done experiments with people with where they had an epileptic surgery, they had electrode implants, and then predictability was much higher. But yes, these were also patients who were drowsy, etc. So anyway, what you will find if you would do this is that you would find something like this, right? So you have task A, situation A, predictability 75%. Task B, it's somewhat lower. Task C, it's somewhat higher, etc., etc. But across all these tasks, what you will find is predictability is somewhere between 50 and 100%. And that's basically, I would argue, makes this task useless in finding out more about free will. And why? So what's a fatal flaw? Okay, so let's say we argue for the position of agent-causal free will. And the idea is you're ultimately in charge to some extent. But of course, you also have a personality, you have habits, you have inclinations, you have automatisms. So nobody would argue you're completely unpredictable. That's just not realistic, right? It's not that every time you meet somebody, you have no idea what to do. People have their own character. People are predictable to a large extent. So the idea of free will is not that you're completely unpredictable. It's just that you're not completely predictable. There's some wiggle space. There's some space where you make your decisions. So your predictability is somewhere between 50 and 100%. And depending on the circumstances, etc., it will either be closer to you being 100% predictable or closer to not being predictable at all. That's what free will argues. Okay, what is argued from the point of view of determinism is, well, no, you're always, in principle, 100% predictable. However, given our current measurement techniques, we will never actually get to 100%, right? We have varying degrees of imprecision, and depends on the exact situation how imprecise we are. So predictability will vary between 50% and 100%. So the problem is, given our current imprecision in measurement techniques, both ideas make exactly the same prediction. So this means, given our current technical capabilities, this approach of trying to predict somebody's choices, that's basically the idea of Libet, that's a dead end. We can do all kinds of experiments, and we have done hundreds of experiments in this line. Yeah, and it basically what I just described is what you see. There's varying degrees of predictability. Sometimes it drops all the way to 50%. Sometimes it goes up higher, and it's completely unclear how we should interpret it. So I would say not only is the issue of free will not solved, we basically have no way forward at this moment. And we do continue doing all these Libet experiments. And in my honest opinion, I mean, I don't want to be too negative, but I don't think that we'll get there given our current technical capabilities. Okay, so then what should we do if this approach doesn't work with the Libet task? How can we test whether people have free will? Okay, so first I'll have to delve into some theory, and then I will propose an idea based on this theoretical musings, basically. Okay, so let's first look at the problem of free will from another angle again. What does determinism come down to? Determinism basically says the brain is a clockwork, or a clockwork plus random noise. But the idea is you as a subject cannot change the course of events. So there's a fixed set of rules, or an altering set of rules. It doesn't really matter, but these rules are not under your control. So the brain operates based on a set of rules, and it just has to execute these rules. You as a subject cannot change anything about that. So what it means, if certain input arrives at your eyes, then subcortical areas have to process this information according to fixed rule or according to a bunch of rules. And this results in, let's say, some activity in the visual cortex. And you cannot avoid it. There's nothing you have to say about that. So it means stimulus, visual percent. And yeah, that of course resonates with our experience indeed. Like if I present you a visual stimulus, you cannot decide what you will perceive. But, and that's the crucial part of determinism, the same is true for the pathway from stimulus to motor cortex. It's exactly the same as a pathway from stimulus to the visual cortex. So you get a stimulus, there's some automatic processing, there's a bunch of rules that process the input, and then that results in motor activity in the motor cortex, and this activity determines what you do, and activity in other places in the cortex determines what you think, etc. And just as with your visual percept, there's nothing you can do about it. Okay, so that's the idea of determinism. And the idea of libertarian free will or agent-causal free will is no, it's not a clockwork. So there's not an unbroken causal chain. You get input. Let's say you get the input to decide between A and B. Then you go into the decision phase. But before the decision, it's really not set yet what will happen. And only after you decide, A or B happens. So the idea here is the causal chain is broken every time you make a decision. And we get out of the break of the causal chain. You decide how the causal chain proceeds after the break, basically. So that's a big difference that's the core distinction between determinism and libertarian free will. Okay, so let me just reiterate that, because that's kind of important for the experiment that I'm proposing, or that we're proposing. Yeah, let me just take a short drink here. So what determinism says is your brain is a clockwork. With one input, it must follow exactly one path to its output. And what free will says, no. Every time you as a subject make a decision, the causal chain is broken. And the subject, you, are the first cause of a new chain of events. Okay, so you might think like, well, this is crazy, you know. That now it might start to dawn on you why so many philosophers and so many neuroscientists don't believe in free will, because this seems really weird, right? A broken causal chain. So we have to say in classical physics, this is also, there's no room for a broken causal chain in classical physics. So in classical physics, basically every physical effect has a physical preceding cause. And this goes all the way back to the Big Bang. So from the Big Bang onwards into infinity, into eternity, everything is set in stone. And there's a causal chain that's not broken. And in that idea, in the idea of classical physics, there's just no room for a subject to make any breaks in the causal chain or to decide anything for herself. So in classical physics, it's just impossible to have free will. Of course, as you saw in the abstract already, this is why quantum physics, in my point of view, is interesting. So this, of course, is the famous Schrödinger cat. And the idea of Schrödinger cat is there's some quantum event, let's say radioactive decay. And if it goes one, and there's 50% chance that the radioactive decay will happen, and 50% won't. And if it will, then some poison is released, etc. A chain of events is set in motion that eventually leads to the death of the cat. And if the radioactive decay does not happen, then the cat remains alive. And what quantum physics basically says is that before you make the measurements, there's a superposition of both. The cat is both dead and alive. But after you do the measurement, only one of the two options remains. So what this means is that in quantum physics, there is a break in the causal chain. So there's a completely deterministic causal chain until you make a measurement, and then there's a gap. Then there's a small jump of indeterminism every time you make a measurement. And that might, I would argue, that's the only place where we can find a break, according to our current knowledge of physics, of course. There's the only place where we can find a break in the causal chain, and this is exactly what we need for free will. So let me spell it out again. So in quantum physics, what is the idea is if you don't do any measurements, so unobserved matter is completely deterministic. So then it's just wave mechanics, wave plus wave plus wave. You get new waves, but the determinism is not broken. Only when there's a measurement, the wave function collapses. So yeah, I'm introducing some new terms here, but yeah, if you're not familiar with the wave function, I'll shortly explain what it means. Otherwise, we can go into it in more detail later on. But the idea is that what we call a particle is, before we measure it, it's a probability wave. And a probability wave is a distribution of, for instance, when you look at location, probability wave is a distribution of how likely it is that you find the particle at a certain location when you measure it. Okay, so the idea is if you don't do a measurement, the only thing you have to work with are probability waves, and despite their name, they're completely deterministic. So determinism is preserved when you don't do a measurement. But whenever you do a measurement, the wave function collapses and indeterminism arises. So there's a small break in the causal chain every time there's a measurement. Okay, so to contrast the two things, classical and quantum physics. In classical physics, the clockwork cannot be broken. There's an unbreakable chain of events all the way back to the Big Bang. But in quantum physics, there's an unbroken chain of events unless a measurement is performed. So every time a measurement is performed, some indeterminism arises.
So I want to clarify something. The fact that someone is performing measurement already seems to suggest a level of free will for someone to make that choice.
Yeah. So that's a really good point. I cannot go into it in too much detail here, but this is also indeed a big discussion they have. So I think this was a discussion between Gerard het Hoofd and some other physicists and philosophers, where his way out of the measure problem was some kind of super determinism. So he would argue like, no. We can explain all this because everything is basically orchestrated or predetermined. Blah, 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 blah. But that's indeed takes away, and this was a counter argument to that, is, then we would never be able to do things like RCTs. If your way out of the results is saying, but it's all basically a giant conspiracy, so to say, because it's all predetermined in the Big Bang and you don't have free choice in doing in your experimental settings, then that might save determinism, but in the face of quantum mechanics, but it basically jeopardizes the whole of science. And so that you can also turn it around, and then it seems that, hey, wait a second, it seems that when we think about, but you can do different experiments and so on, that to some extent we may presuppose that the experimenter has some kind of free will. So this is an interesting argument, but it's also a very complicated argument. So unfortunately, I cannot go into that into detail here. But that's a good point. Thanks. Okay, so anyway, the main point I want to make here is that in quantum physics, you could argue that the causal chain is broken. Every time there's a measurement, there's a break in the causal chain. The problem is this does not give you free will, not per se, because these indeterministic jumps that happen during measurements, they're not under your control. So when you do a measurement and there's a breaking of the causal chain, okay, but you don't control, it's just adding random noise from your perspective. And in a way, this makes sense, right? Because generally, you don't have free will. So when there are events in the outside world, so when you do a measurement in the outside world, you don't have telekinetic powers or something. You don't directly control the outside world. And even more, even in your own body and brain, most events you have no control over. So you don't directly control your heart rate, you don't directly control subcortical areas, you don't control the glia cells in your brain. You don't even control what most neurons in V1 do in response to visual stimulation, and so on. So yes, it's true that generally there may be an indeterministic jump, but it doesn't buy you any control. It doesn't give you any sense of free will or any kind of free will. So that's not all. So we're not there yet. We cannot just invoke quantum mechanics, say, hey, there you have free will. Something more is needed. So let me reiterate that. So the collapses of the wave function in quantum physics are the only known events to break the causal chain. So far as we know right now, everything is completely deterministic except measurements in quantum physics. And libertarian free will asserts you control these breaks if and only if. So the two F's here is not a printing error. That's shorthand for if and only if. They are so you control these breaks in the causal chain only if they are the cause of your voluntary behavior. So when do you have free will? In case, not all, mostly you don't have free will, but the idea of free will is that you control your voluntary behavior. So when you, without any outside coercion, when you decide to move your hands or your body, whatever, that is part of voluntary behavior, but it can also be covert, right? So you can decide to think about something. And if these are not like obsessive thoughts or whatever, then you have some kind of control, some kind of voluntary, agency in that sense. And the idea is that, so libertarian free will asserts that only in these cases where we have the intuition of control, that's where you actually have control. So to specify this a little bit more, okay, so where we know, of course, a lot about the neural correlates of voluntary behavior. So for instance, when you make a voluntary movement, so an overt motion, where does it start? Well, it mainly starts in frontal areas. When you engage in voluntary imagination, so voluntary covert behavior, we don't know exactly. It seems, by the way, also to start mainly in frontal areas, but it could also maybe ignite to some extent in the occipital areas. But what we know for sure, it all happens in the cortex. All voluntary behavior originates in the cortex. And the idea is then as follows. Okay, we have these collapses of the wave function. We have these indeterministic jumps. Generally, they are not under your control. So when they happen in the outside world, when they happen in subcortical areas and so on, you have no, just some random noise that's added. However, when they happen in the areas that are the starting point of your voluntary behavior, now you control these collapses of the wave function. So only in the case that a wave function describes or is associated with matter in, let's say, the frontal cortical area, and if the transition from wave function to actual particles is the starting point of some kind of voluntary action, only in that case, the subject is in control of the transition from wave function to actuality. So yes, there's indeterminism rises all the time, but it's generally not under control of the subject, but only in the case when the indeterminism arises in frontal cortical areas, for instance, only then the subject is in control of its indeterminism. Okay, so now we're finally getting to the central thesis. So it took me a little bit longer than I hoped, but I think I can also still get to the experiment, of course. So the central thesis, we're almost there. So the idea is that voluntary, overt, and covert behavior probably starts in frontal cortical areas. And only in these cases, the subject has free will, in the case of voluntary behavior. So only in these cases, the subject controls the breaks in the causal chain. And so to make it clear what we're talking about, this is the idea that we are going to investigate. The idea is humans have non-random control over collapses in the wave function when they occur in certain areas of the human cortex. So the idea is that we can control indeterministic collapses. And yeah, of course, that sounds crazy, right? So it's like, what? Okay, so one thing is that there are even indeterministic collapses. And now we're adding more to the picture where we're saying, no, in some cases, humans even control these indeterministic collapses. Okay, it's true, it does sound crazy. But the thing is, this is currently the only known option for libertarian free will. The idea here is, well, the causal chain is only broken during collapses of the wave function. So that's the only window for free will. Free will is only present during voluntary behavior. Voluntary behavior starts from the human cortex. Therefore, the only way, given our current physical knowledge, current knowledge of physics, that humans have libertarian free will is if they control collapses of the wave function when they occur in certain cortical areas. So basically, I would argue this is the ultimate test for free will, given our current knowledge. So either humans have non-random control over collapses of the wave function in the human cortex, or libertarian free will does not exist. That's given our current knowledge. So of course, our knowledge can change. then this is no longer applicable. But if our current knowledge of physics is correct, then these are the only two options. And you may say, yeah, this sounds crazy. Yes, it does. But libertarian free will does not exist. It does not exist, meaning you are basically a mechanical robot that has no control over, no ultimate control over your own thoughts and behavior. Well, that to some people sounds crazy as well. So there's no easy way out here, so to say. Okay, so what are the contrasting predictions here? According to determinism, voluntary behavior is nothing special, and the collapse of the wave function is always random. It's never under control of the subject. It doesn't matter if it happens in the cortex or wherever. According to the idea of free will, if and only if collapses of the wave function cause voluntary behavior, which means wave function collapses in the frontal cortical areas, then they are non-randomly controlled by the human subject. Okay, so hopefully it's somewhat clear why we want to do this experiment, but then you might think, okay, well, that's maybe fun to think about, but how will you ever investigate this? So how can we test this? Clearly, we cannot put a measurement device inside a human skull. However, what we can do is we can entangle photons with neural matter. So there are some physicists here, so this is good. So I think, well, I mean, maybe you're not all equally familiar with it, but the basic idea is pretty straightforward. And entanglement simply means that two or more particles have interacted, and they are now described by one wave function. So this is an example of where people tested Bell's theorem, Bell's inequality, and Bell's inequality was violated there. And the idea there was, I think, it was conservation. So you have entanglement, but you still have all these conservation laws. I think this was conservation of spin that they investigated. And the idea is that you have two particles, and you have conservation of spin. So for simplicity, I will just, I'm not sure it is exactly correct, but let's say if one has spin up, the other one also has spin up, and there's three types of spin. And the idea is then that before the measurement, so you have the source here where the two electrons are leaving in opposite directions. Before you measure them, actually, they both don't have a spin yet. So they both are in superposition of spin up and spin down. But as soon as you measure this one and he gets spin up, then this one here also gets spin up, but not before that. So you might say, okay, how can you test whether it wasn't already the case before that? Well, that's Bell's theorem. It's actually not that complicated, but I simply don't have the time to go into that. But they basically, was with Alain Aspect and other people, they've basically shown, yes, this entanglement is real. It's really true that when these two particles have interacted in a way like this, where there's some conservation law at play, then there's one wave function that describes both of them, and when the features of one particle are determined, the features of another particle are immediately determined as well. So now the fates of the two particles are linked to each other, and if something happens to this particle, it immediately, forget about speed of light, etc., it doesn't matter anymore, it immediately affects this particle as well. Okay, so that's the basic idea of entanglement. You have one wave function that describes features of two particles. And when the wave function collapses, the features of both particles are determined instantaneously. And the crucial part here are the conservation laws, like conservation of momentum, conservation of spin, etc. They still hold. And this means that the features of both particles are coupled. Okay, so this is great for our experiment because now we have a way. Okay, we cannot put a measurement device around neural matter, but what we can do is we can entangle neural matter with photons. And now basically the fates of the two pieces of matter are linked to each other. And we can measure these photons, right? So these photons first go into the cortex, then they go out again, and we can measure what happens to these photons. So the idea is if humans control the features of one of the two, and in this case, that's neural matter, of course, they also control the features of the other to some extent. So that's the basic idea. And how can we do that? So the good thing is that this is, well, not extremely recent, but it happened a few decades ago. They started to do brain measurements with near-infrared photons, and it's called near-infrared spectroscopy. And how does near-infrared spectroscopy work? You have a source of photons of a wavelength of around 780 nanometers, so just outside this visible spectrum. The good thing is of these photons is that they penetrate the skull. So they basically don't interact a lot with the skull. Then they go through the skull. Then they interact with the cortex, and then they exit again. And that's a great thing, because now we can do measurements of the brain with these photons. And the other great thing is that, yes, most of you will probably know this, these are low energy photons. So this is not ionized radiation. So it's not harmful. It cannot cause cell damage. So this is a completely safe way of sending, let's say you would use gamma rays, it would be extremely harmful. You cannot do that. And near infrared photons is completely safe. So that's the upside. And in fact, yes, near-infrared spectroscopy at this point is widely used. And as I said, it's completely safe. And the whole idea is simply infrared photons penetrate the skull, they interact with neural matter, and they exit the skull again. Okay, so what is the experiment setup? It's actually pretty straightforward. We'll have, so we're building that right now. We have a near-infrared laser at low power, of course. Otherwise, yeah, cannot cause cell damage, but you can get skin burns. So you still have to have a low power there. And we just basically use the specs that you use it in a near-infrared spectroscopy as well. The photons exit the skull, and they are recorded by the camera here. And what the camera records is depicted on a screen that the participant sees. And now it basically changes into some kind of neurofeedback experiment, where the subject is just asked, do something to change the pattern of the photons that hit the camera. Okay, so to reiterate that, the photons are entangled with cortical matter. These entangled photons are subsequently measured. Subjects see the results of this measurement, and they are instructed to affect the outcome. So it's very similar to a neurofeedback task. The idea is, and this is the crucial part, if they control wave function collapses of the entangled neural matter, they can also influence the photons. So yes, if these photons are entangled with matter in frontal cortical areas, and this just happens to be by chance the matter that's involved in voluntary behavior, then the subject controls this matter. And because it's entangled with these photons, it also controls the photons to some extent. Okay, so to sum up, the central question is, when it comes to voluntary behavior, can humans non-randomly break the causal chain? And in our experiment, this boils down to practically, can humans non-randomly affect the collapse of a wave function associated with neural matter plus their infrared their entangled infrared photons, and we only, of course, measure this part of the equation. All right, that's it, and thank you for your attention.
I'm quite a mind-boggling kind of idea, I guess. Is it really possible that to entangle this photon and then project it into the cortex? I just don't know how what the plausibility of this idea. I mean, from physicist point of view or empirical point of view, is there any kind of comments?
You want me to comment, or you want to?
Yeah, first of all, yeah, from your end.
Yeah, so I think this is a great question, and it's also a very critical question. And I think this is, I think we only have like 10 minutes now, so it's probably too short to really discuss it into detail.
It's fine. I'll be here.
Yeah, okay.
Yeah.
All right. Yeah, so I'm just spitballing here. So the basic idea is that, so this is also basically, I wouldn't say this is completely set. It's the same as with a measurement problem. There's lots of different ideas about this. And what it basically has to do with a lot is decoherence, in my point of view. So what you see in decoherence is that this is, of course, when a particle interacts with lots of other particles, right? And decoherence, for instance, what it does is it kills the interference pattern. So if you have a photon going through two slits, if that photon is entangled with lots of other matter, it will no longer produce an interference pattern. So there were some initial ideas like, hey, decoherence can explain the measurement problem. I think now mostly people have kind of walked away from that idea, because what if you, to become a little bit more detailistic, if you have the density matrix, basically, then what decoherence does, it kills all the off-diagonal terms. So that's basically kills the interference parts. But the superposition, the diagonal terms are still there. And if you translate that back into a photon going through two slits, then there's no longer the first order interference of the photon with itself, but there's still a superposition where the photon either goes to the left slit or the right slit. It's still a superposition of both. And this superposition is not resolved simply by decoherence. So something else is needed there. And that's where the many worlds interpretation comes from, right? So the many worlds interpretation says, oh yeah, okay, decoherence plus a splitting of the universes solves it. Well, I'm not personally a big fan of the many worlds interpretation, but that's an idea. And that kind of goes to the entanglement idea as well. So the entanglement is broken every time you do a measurement. So after the measurements, particles go their merry ways. But decoherence by itself, it will kill off first order, second order, whatever order interference patterns. But decoherence by itself just means a bigger and bigger wave function.
Yeah, but
so just by itself,
maybe my question was actually really considering all these things, even if you can entangle this, you use this entanglement things on the photon when you project it onto the skull or the brain. Can you still observe anything that you wanted to observe?
It's
empirically.
One step more practical. So we're setting this up right now, so my intuition is yes. So what we have set up, and I don't know if Josella is still here, but
I am.
Oh, you're still here. Oh, okay, I didn't see you in the list. Anyway, so Josella is basically actually making the actual setup. And practical things, I'm sure she can tell you a lot more than I can. But I think what we have done some reflection. So in a way, what you're doing is just reflecting it off materials. When you reflect it, and this is of course a very inefficient material, right? The brain is very inefficient reflector. But yeah, you have to do some filter first. So if you just let the photons pass from all sides, it becomes a blur. So you have to put a diaphragm there. So you select one direction, for instance. But then, yes, then you can still see a diffusion pattern or even interference pattern.
Okay.
So we have already got these results, not with brains, but with other inefficient or somewhat inefficient reflectors.
I don't know. Okay. So Ben and Ariel had some kind of comments in the chat box. But maybe Kavan or anybody you want to ask question first, or maybe Ben, do you want to go second?
I'm happy to ask a question or two. So, I mean, I agree with you. So first of all, let me say that this sounds very exciting. But now I'm going to give you some critical questions because being a physicist, I'm pretty uncomfortable with any choice that I have. On one hand, I don't like many world interpretation, but on the other hand, I don't like ad hoc collapse of the wave function either, because having a purely unitary universe is much more interesting and reasonable, because otherwise you have to put in another collapse term by hand, and then you can always enlarge the universe and say that there is another pure universe where no collapse happens. In either case, there are these so-called loopholes for Bell's inequality experiments. You can close all of the loopholes, but there is one loophole that you cannot close, which is superdeterminism. And then we're back to where we started.
Right.
And so, on one hand, I think this gets us closer to an answer, but in a way, not really, because there is that loophole that's basically unaddressable. Now, the other thing I wanted to ask was that's kind of related, is that it seems to me that you require a first free will in analogy to a first cause. So for 10 billion years, there is no free will. Then there is some intelligent being that appears through evolution, and all of a sudden there is free will, and then free will multiplies. But for most of the age of the universe, as far as we know, not knowing that there are other intelligent beings, there was no free will. Is that correct?
Yeah, I think that's kind of painted myself into that corner. Yeah.
Okay.
Yeah, I agree with you. These are all crazy ideas, but I would say there's just no non-crazy way out. That's a problem. Like, yeah, of course, we would like to have our cake and eat it too. Like, it's all just very simple, and we can hold on to all our dearest intuitions. Yeah, that would be great. But unfortunately, I think we will have to dive into one rabbit hole or the other.
Okay, Ben?
I mean, can I just add one more comment? Yeah. I would say that the quantum measurement problem, I'm not an expert on it, but this is my interpretation of it, is effectively this problem, that on one hand, we want this deterministic world that Newton and Descartes are responsible for. On the other hand, that also annoys us. And quantum mechanics requires that we have to come in from the outside and make a measurement. So it breaks this whole idea of determinism. And that's the annoying bit about the quantum measurement problem. But I think the same problem exists as far as in the old classical world. If everything is clockwork, how do we not also follow that clockwork rules? And how do we have free will? So I don't think we're going to ever get to eat our cake.
Yes, thanks.
Yes, I had one question about the measurement or the experiment, which is like, it's very, very hard to get entanglement to last a long time or to go long distances. You know, they go right down to 0 Kelvin, as I understand. And, you know, it's really fiddly and you might spend years getting it. So to do it at room temperature and just fire a photon into someone's brain and hope that you get long-lasting entanglement enough to, you know, make some sort of inference. Have you kind of done the calculation on what time scale you might expect, or are you going to put this person down to 0 Kelvin?
Yeah, we're just yeah. Well, it's kind of stressful for the participant, but I'm sure they'll be fine. No. So yeah, I don't think, I'm not sure that entanglement. So it's the same with these quantum computers. So that's basically I kind of try to address it when and with Nao's question as well. So the idea is, of course, with quantum computing, which is also done at like really low temperatures, etc. So is to control the entanglement. It doesn't mean that you don't have entanglement otherwise. Indeed, this is the problem of decoherence. And this to some extent cannot be avoided. I'm actually not so sure that. So they have done some, Kavan referred to that as well, the loophole experiments, of course, which they have done actually in the Netherlands, they've done quite a lot of those loophole experiments, as you probably know, where they entangle photons with electrons. I don't think they actually did this at really cold temperatures. So the idea of these cold temperatures is simply to bring the number of interactions down, right? So what you lose control of the entanglement once there's billions of interactions, because you no longer know what is. So if you want to have either want to do quantum computing or you want to have precise measurements, then you don't want your entanglement to involve billions and billions of particles, because there's now, billionth order interference patterns that you can never pick up anymore. So basically, you just want to reduce the number of interactions. But that doesn't mean you have to go down to 0 Kelvin, basically. You can also, with light, sometimes, if you, depending on your setup, I mean, light by itself, you send it through, you don't have to be in vacuum even. You can have, normal two-slit experiments are not done at 0 Kelvin in vacuum or something. They're just done at room temperature with normal distribution of air. And still you don't have so much interaction that the interference patterns are killed. And I'm sure you're aware of the phenomenon of thin film interference. So what you can do is, and this is a very well-known phenomenon, is that you let light be reflected by inefficient reflectors. Basically, that's what it comes down to in water. It can also be in solid materials and so on, and you can get all kinds of interference patterns. So simply these interactions with, and these are hot macro objects basically, this does not kill off the interference patterns yet, and this does not. This by itself does not constitute what you could say. So, or maybe I'm kind of unclear here, but the main point I want to make is that when you look at it theoretically, the only thing that kills entanglements is a measurement, actually not decoherence. It just increases the number of particles that is part of the entangled wave. So in that sense, yeah, it depends on whether measurements happen immediately, but there are reasons to believe that this, yeah, I mean, this does get us into like some philosophical difficult territory, because yeah, there's a lot of debate about what measurement is basically, but it's not completely clear that every time at room temperature photons interact with a big object, there's a measurement basically.
But also specifically what you would want to entangle, like even if you could go in right to the neuron, where would you fire it? You know, like
Yeah,
just throwing it right into the brain, and it seems a little less specific than you'd want to really test the hypothesis.
Yeah, no, that's of course that's a really good point. I completely agree with that. In a way, it's a downside, and but on the other hand, you could even say it's an upside at this stage, because what we do now is we basically shoot a lot of hail, right? Like we basically, it's not sniping what we're doing. It's not sharpshooting. So we're basically having a photon that entangles very widely with all kinds of neural matter, and we're looking for a small statistical effect. And if we just happen to entangle it with some neural matter that's involved in these free choices, basically, then we over, many trials and so on, we can find a small statistical effect. Or not, I mean, it might just be a pipe dream. But if we do find it, then indeed, of course, it becomes, okay, what are we actually looking at here? And then indeed, we want to become much more precise and so on. So I do have ideas about that. I mean, to become extremely precise is challenging. So now we just have a continuous wave laser. But I'm not sure how familiar you are with functional neural infrared spectroscopy, but they are looking at these kind of things there as well. So you have something called temporal domain mirrors. And what you do there, for instance, is you use a picoburst laser. So you send a signal into the brain only for like a few picoseconds, actually 50 picoseconds. And you have a camera, you can just get them commercially right now, that have nanosecond precision. And now all of a sudden, the path that the photon can take to still be in time for the nanosecond precision is very much reduced. So you still have uncertainty, but you very much reduce the uncertainty. So then now you can zoom in more on which cortical matter is actually relevant.
I see. So that also probably answers to some extent my question as well. So you are basically hoping that if you shine the light through the frontal areas and then get it from there, then you would hope that some kind of effect is maximally observed. But if you shine it in somewhere else, like the back of the brain or cerebellum or something, that more or less controls the temperature issue or kind of tissue issue, you would find much less of that kind of effect.
Yes,
I see.
That's exactly right.
Then I think, as long as there is some entanglement and some kind of measurement effects, then, if you repeat it many, many times, it seems, in principle, detectable to me.
Yeah, that's the idea. But I mean, I see Josella smiling, but yeah, so with Josella and I discussed this a lot as well. I mean, the actual reality, as you guys all know, is that you start out with all these high hopes, then you start doing experiments and you run into lots of things. So I'm sure we'll still run into many challenges. It's just the idea, indeed, as you say now. So there might be some light at the end of the tunnel. That's what we're aiming for, basically. If we'll really get there, we'll see. We'll find out.
So what would happen? So let me see if I understand what you're doing. So you're sending in entangled light into somewhere in the brain. Now, what happens to the other photon?
No. So the photon becomes entangled with the neural matter. That's the idea. So basically, it's a very similar to the setup they had in Delft, where they looked at what you refer to the loopholes of Bell theorem, where they entangle photons with electrons. So basically, that's what we're doing. We're entangling photons either with electrons or other, well, mainly electrons. And these electrons are part of, let's say, a larger wave function of cortical matter.
So are you using a single photon source or an SPDC or?
No, so we're using a continuous wave laser. So we're sending in a shipload of photons, and a shipload of photons come out again.
But you're not squeezing it or anything.
Squeezing? What do you mean?
You're not squeezing the laser.
Well, since I don't know what squeezing the laser means, I would have to say no.
Okay, so I mean, a continuous wave laser, the way you enhance this quantum profile is by squeezing it along one of the direction. So you have this phase space representation. So it looks like a ball in the XP space, and then you squeeze it, and that amounts to a type of an entanglement. And so for instance, in LIGO, they use that in order to boost the signal above the noise threshold. Now, the reason I'm asking that is, so I mean, what I was wondering is that can you then somehow have a control experiment where you don't have any entanglement. You have just random noise between the electrons and the photons. Or yet another experiment where you have classical correlations. So in other words, you send in exactly one directional polarization, or a very monochromatic polarized light. And would that then lead to some different behavior? Because I mean, how do you know that entanglement is responsible for anything at the end of the day in the results?
These are excellent remarks. This is really good stuff. Thanks. Yeah, so I think these are really good points indeed. Yeah. So what we want to exclude classical explanations, right? If it's just like, hey, there's just some classical stuff going on, and that can explain all the. I mean, we do know people can do neurofeedback. That's completely classical. I haven't really thought about what you're saying here, but this does sound very interesting. I have some other ideas about how to differentiate between classical and quantum explanations, but I think these are really good ideas, to be honest. So I mean, this is a work in progress. So we'll definitely think about that. Thanks, man. That's really good. Yeah.
Okay.
I have a fairly naive question.
All right.
About the use of the word you, because when you say you do, or you collapse the wave function, or you control, when I think of you, I think it's my brain and it's my, but you're saying that there is some, like, what's left? Is it some spiritual dimension? If it's not physical and you control your own cortexes, like, what is the me that's controlling my cortex if not the me that has the cortex, So,
right. So I see Ariel turning on as well. I think it's very related to your question, right, Ariel? So does libertarian free will presuppose a particular theory of consciousness? As far as I can tell, it seems to require a non-functionalist and quantum-compatible theory of consciousness. I think I would have to agree with your remark, Ariel. So I guess if you indeed, I mean, this of course is much more on a philosophical side of things, but yeah, indeed, if you go for the option, yes, you are a computer program basically, or like a set of functions, which is basically functionalism. Yeah, no, then this whole enterprise is basically a dead end. I agree with that. So you require a non-functionalist and quantum-compatible theory of consciousness. I think that's basically a good how do you say, summary. How do I see Yeah, exactly. Yeah. So you want to distinguish between that, right? So you don't want, this is not a panpsychist theory or something. So what I'm not chasing some kind of panpsychist idea here. This really comes down to, it's focused on when you make, okay, I won't define the subject. So what is a subject? Okay, I won't define that here. But I mean, honestly, I had this, it's kind of a sidetrack, but I had a discussion with somebody about, how do you define this? How do you define? Most phenomena that are somewhat interesting are not easy to define. Even something like attention or something, you can say, hey, is that just what happens in visual search? No, that's not just what happens. We use visual search to measure attention, but it's not the same thing. And unless you have something that's very trivial, it's generally very hard to define. You can just give examples. At least that's how I think about it. And I would argue the same thing here with the subject is like, so what are you? I would keep it as minimal as possible. I would say, like, what I mean by the subject is just you as an experiencer. So you have all kinds of sensory experiences and so on. And on the other hand, you as seemingly a decider, right? Like, you're not just a passive being. It could be an illusion, but you have the idea that you sometimes make voluntary choices. So and into that, there's no, this whole story is just focused on that. When you make what to seem to you voluntary decisions, that's what I'm focused on with this idea here. But that's pretty standard.
If it just seems like it but isn't, then that wouldn't require any of this, right? That could all be classical.
Yeah. So indeed, if it seems like you have free will, but you don't, then of course it falls apart. Yeah, true. Yeah.
But there's a claim that it really is, and that I can control my cortex in a way where the I isn't the thing with the cortex. Ariel can do this better than my naive.
Yeah. And to also go on into it a little bit more about the or, is this a version of or? I wouldn't say it's a version of or because I think it's a little bit the other way around. So or basically says that indeterminism during quantum measurements causes consciousness. And here, this is much closer to the consciousness collapses idea, where it's like, no, consciousness causes indeterminism. So it's the causal order is reversed, compared to or.
I also thought that the or assumes that this kind of collapse happens really regularly, right? And at many different locations, regardless of the whether you make a free choice or not, or whatever.
Yes, that's true. That's totally true. But so in or there's no real connection to free will.
Yeah, and maybe Ariel, was that satisfactory to you? Or?
Yeah, that pretty much answered my question. I've got more, but the physicists will have better questions, so they should go first.
There is also one comment from YouTube, if it's okay. Fine. So I'll read it.
Yeah, go ahead.
I read it. Julia Sagar, Vaitek Vidyasagar says, there can be no prediction which you will be right to believe and wrong to disbelieve. So my question is, this idea of Mackay, in principle, not different from measurement of quantum mechanics? I don't know.
Can you say it again? It's kind of, I could not completely follow that. This
the last
idea
one,
of Mackay?
Mackay. M-A-C-K-A-Y.
Oh, Mackay.
Mackay.
There can be no prediction to disbelief. Okay, so I think this questioner is referring to the prediction paradox. So the prediction paradox, I'm not completely sure, so I might be answering the wrong question here, but I think we should be right.
I don't know, because there is no person here. It's not possible to ask a clarification.
So I'll just go out on a limb and I'll just assume that what the questioner is referring to is the idea of the prediction paradox. And the prediction paradox is that you can be completely deterministic. I can make a robot that dodges prediction, right? So I can make a robot that if you say to the robot, you will do A, then it will do B and vice versa. So I don't think that's the same thing as but that's not real indeterminism, right? So the prediction paradox does not require any real indeterminism. So in that sense, yeah, that is very different than, I would say, if that's the idea of McKay, then I would say that's very different than measurement in quantum mechanics. So the claim, at least, of measurements in quantum mechanics, and yeah, it's under debate, but it's not completely crazy to say yes, there's actual indeterminism arising during quantum measurements. And that's different than the prediction paradox. You can solve the prediction paradox without any indeterminism, basically. So if I interpret the question correctly, I would say, yeah, no, there actually is a difference between this idea of McKay and measurements in quantum physics.
Okay, that's fine. Is there any questions from the audience in Zoom or YouTube? Any more? And Josela, do you want to say something or fine?
I'm totally fine. I enjoyed all your comments and I marked them down, and I think we will soon discuss all of them. Yeah, so I think it really helped. It's really a nice group of people here. Yeah.
Okay. There is another question.
Can I add to that as well now? So I just want to say I'm also really happy with these comments. I'm also really happy that you took the time to listen to this. And I also want to stress, so of course now has my contact details. So I really enjoy, of course, all your feedback. I think there's lots of really great ideas there. And feel free to, if you have a suggestion or a comment or a further discussion, feel free to send me an email, of course. That's what I want to put forward.
There was one last question in the chat box. Can you see? Without quantum physics, there are always spontaneous activity in the brain. The frontal cortex could pick it up by chance and lead to behavioral action. Could this be a free will?
Yeah. So this is a good question. So yeah, this would not be free will, because that's basically just well, it would lead. So this is a really good question, because it stresses the difference between unpredictability and free will. So yeah, if you have a completely random source, yeah, you can generate very random numbers that are really unpredictable. However, clearly, if you just use some kind of random noise source that you do not control, then it's like adding random noise to determinism. So that would not be the same as free will. It's really you have to be in control.
So, I mean, on that note, what are your thoughts on the Penrose-Hameroff idea? Because that to me seems, as much as I don't like it, it seems kind of reasonable, because you have a truly random event inside the brain that allows you to make a random choice, and that to me is as free as it gets, that you are able to choose randomly, independently of anything external. The cause is something internal, and it's intrinsic to the collapse model of the universe, that there is the pure quantum mechanics doesn't exist.
Right. Yeah, that's a good question. So I guess it really depends on the details of how that is worked out. Because I mean, definitely in the generally I would like to zoom out before I answer your question. The Orch-Orr model to me at this point seems not very intuitively appealing. So I don't think, I mean, that doesn't mean like the broader idea is false, but like this specific implementation, I think will not pan out with the microtubules and stuff. I just don't think that's how the brain works.
Never mind those details.
Never mind those details. I agree. Like, let's look at it at a more conceptual level. I guess to some extent that's it could be the case. Like if your consciousness is instantiated in certain events, and the same events drive your choices, or they're correlated, then that could give you some kind of control. But it really depends on how that's panned out, because the alternative is, and that's Robert Kane's idea of free will, and I think what's it called again? Event-causal libertarian free will. But this, I think, so I am really talking about agent-causal libertarian free will. So event-causal libertarian free will, the idea there is that external events that you have no control over just add random noise, and that causes unpredictability. But yeah, this is also the criticism that Robert Kane, of course, has received. This does not seem like free will, right? Because it's not
but
this
is slightly different, right? Because it is
different
in the brain, so it's not an external noise. It's just saying that there's a fundamental process in the brain that is quantum mechanical, which then is subjected to collapse model, which is intrinsically random, and therefore, you have pure randomness source inside your brain. Because in classical physics, where do you get randomness from, other than pseudo randomness? And
no, that's true. So as I said, like it depends on how.
Yeah.
So this could, I guess, in principle work. It just depends on how it's filled in exactly. Yeah. Whether you end, and it depends on how you implement this. Whether you end up with agent-causal or event-causal libertarian free will.
But by the way, a question on that: like, have you been? So there's a lot of movement in quantum mechanics and quantum information theory about causal modeling, and in a way, I can so people reinterpret Bell's experiment in terms of a causal model, and in a way, I can say that your proposal, I can simply replace the classical cause with quantum cause, and
what did you say? You.
So if a quantum if I have a quantum particle meeting another quantum particle leading to a quantum effect, then I can call it a quantum cause. And so you have a bit more mechanics, you have a bit more richness than classical causal modeling. But effectively, it's the same, right? There's, you still have the same issues as there's no first cause, et cetera, the same arguments, at least. And from that angle, I kind of like the, if there is free will, then I kind of like the Penrose Hameroff idea, because there has to be randomness somewhere inside the brain. I don't see a way around it. So the question was, are you following the quantum causal modeling literature? If not,
no,
might be interesting.
Unfortunately not.
Okay.
Yeah, that's a good tip. Yeah, I haven't read up on that.
I'd be happy to send some references.
Yeah, please do. Please do.
Yeah, Kavan is the specialist on this one as well. All right, so with that, I think it's good to conclude. Thanks a lot, Yair.
Yeah, thanks now. Thanks for your this great opportunity, and thanks for all the interesting comments. And it was really fun to see you in your lab again. So, to see you again and see your lab for the first time.
Yeah. Thanks a lot.
I really enjoyed it.
Yeah.
All right. Yes. Thank you.
Bye-bye.
Bye-bye.